Hello, everybody. Welcome to the first Computer Science Club video session. The idea for this session is that we have people spread across multiple offices, and it was becoming increasingly hard for people to, in synchrony, attend to the Computer Science Club sessions. So the idea now is that we have these short videos where we can explore some interesting subject, and then you can watch it in your own time, and then later we can use Slack channels to discuss the topics, doubts, references, whatever. So the topic for today, since there's a lot of people asking about machine learning algorithms, we are talking about crystal balls and how to predict the future. And we are going to use a particular algorithm called logistic regression. So without any further ado, let's see. Okay, so here we have a Jupyter Notebook that I'm going to use to illustrate the principles for logistic regression. But what are we about to see? We have a data set that's available on the internet that captures information about several attributes for several people. And we're going to guess if they receive more than 50K a year or less than 50K a year. So that's what our crystal ball needs to guess. Do these people receive a lot of money or little money yearly? And which are the factors that are relevant for that? So the very first thing is that we need to go into the data set and try to have a feeling for if the data that we have in there is relevant or not before we even start creating our crystal ball. Because one of the rules of thumb in machine learning is that, in data science in general, it's if garbage goes in, garbage goes out. So our crystal ball needs to be trained based on valuable, relevant information. So I have already prepared this Jupyter Notebook. In a different session, we can delve into the details about what a Jupyter Notebook is or not. But basically for this session, it will be the tool that we're going to use to explore the data set, run some Python code, see the outputs, and then build the crystal ball, build the logistic regression algorithm. So first, let's do some exploratory analysis where we are opening up a CSV file and we're looking inside. Every data is dirty, so we need to clean it up. So what you're seeing here is that originally we had 21,790 entries, but after we clean it up, we get just 20,000. Okay, and basically, what are the information that is available? So our crystal ball will try to guess the future, not based on the month you were born, or on leaves on a tree, or the inside of animals. We're going to use these attributes. So your age, your work class, your level of education, your marital status, your occupation, relationship, race, capital gain, capital loss, hours per week that you work, and the country in which you were born. So these were the informations that were available. They were the independent variables, and the dependent variable is either you received above 50K or below 50K. That's it. So let's continue. So this is just the way each of these 20,000 records look like. So we have, for instance, a given person, anonymous person that has age 29, his work class works for the state. It has a bachelor education, never married, blah, blah, blah. So another way is to look at the whole data set and try to see, for example, for the age attributes. On average, people are 40 years old, but the standard deviation is kind of 12. So it means that we have people that have 40 years minus 12 years or plus 12 years. The person that's the youngest has 17 years old, and the oldest has 90 years old. So in here, you can have get an idea about the distribution of values in our data set. These are other examples. Something that you really need to take into consideration is if the classes are balanced. And in our case, they are not really balanced. So people with high income, above 50K, it's the majority. Oh, I'm sorry, it's the minority. We only have 31% people receiving high salaries and 68% people receiving low salaries. So depending on the distribution of classes, you might need to use a different algorithm for highly unbalanced classes. So there are many ways we can kind of explore the data set to have a feeling about how those attributes influence the dependent variable. So one technique is to create this correlation matrix where you see if one attribute it's highly correlated with the other one. So on the diagonal, you're seeing like age is of course strong correlated with age because it's the same attribute. So that's why we see a high correlation, dark value on the diagonal. But then we can see some other attributes that are kind of interesting. For example, this guy here, it's meaning if the person was born in the Philippines, then it's highly correlated if that person is either Asian or lives in the Pacific or in an island, of course, because Philippines is there. Other things that are highly correlated is that if you have a wife or you're married and then you have kids, so these things are attributes that vary together. And there are others that are inversely correlated. Like if you live in Guatemala, it's unlikely that you live in the United States, for example. Other ways to try to explore the influence of attributes is to create a pair plot. So in the pair plot, we're trying to figure out if the two values for the target variable, the dependent variable, which in our case is the income, what we're trying to guess. If it's high income is green, low income is blue. So by comparing the distribution of two attributes like age against hours per week. So here we see the distribution of high income and low income according to these two parameters. And if they are really separate, if you see all the greens on one corner, all the blues on the other corner, that means those particular attributes are good candidates for our crystal ball to use. So in this case, none of the attributes are really easy to separate. They don't separate well blue and green. So that means we need really to take many attributes into consideration. We have other explorations that we can do. For instance, we can have a single attribute and try to explore all the values for that attribute. For example, if you are working in the private sector, you have this separation between high income and low income. But if you're working for the state government, we have less values. So in here, we can identify two things: the separation for the target variable according a single value for the attribute work class, and as well for all the values for the work class attributes, which ones has more samples in our population of values. There are some that are more obvious than others. For example, occupation. So if you're working on a craft repair occupation, it's more likely that you have a low income than a higher income. But if you have some specialization, it's more likely that you have a higher income than a lower income. and education, blah, 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 or country. And this is interesting. So this diagram is showing us that we have many more values for people living in the United States than for people living in other countries. So using the native country attributes, it's a poor indication for conclusions because our sample, it's very imbalanced regarding that particular variable. And one thing that you can do in that case, you can eliminate the most unbalanced class and examine the others. And then you can see that Philippines has a good balance, but other countries such as China or Peru, they are very unbalanced. Okay, so now that we know the data that we're going to use, the input for the crystal ball, what is the algorithm that we're trying to use to learn from this data and then try to extrapolate for new data to become a true crystal ball that will predict, given those new values for those attributes, if that particular person have a high income or low income. So today we're going to use logistic regression and insight. I'm not going to delve into the full math, but I try to give you the idea, the spirit of the algorithm. So in this example, you are calculating the probability based on data of a single person, given the number of hours that that person studies, the probability that that person will pass the exam or fail the exam. So that's a critical thing about logistic regression. So binomial logistic regression, which is the kind of regression we're going to work today, we are going to study today, it's basically useful for binary guesses, true or false, high or low, pass or fail, health or sick. So in this case, we are applying logistic regression to, does the person pass or fail the exams? So we calculate the probability, and it's kind of obvious that if you do not study at all, chances are that you'll fail the exam. If you study a lot, chances are that you'll succeed, that you'll pass the exam. There is a region in between that this progression is almost linear, but if you study just a little more, chances are you're going to fail. And if you want to do increments when you're studying a lot, then you have to increase a lot the number of hours to guarantee that your grades will increase. So the behavior, it's not fully linear. It has a linear region, but on the edges, then there is a lot of effort to see an increase, and sometimes just a little effort causes a great increase. So that's the spirit behind logistic regression. So what we're going to do is try to compute this function for those attributes. And then we're going to identify a threshold that could be 50% right in the middle of this curve. So if we find that the probability is above that threshold, we're going to say true. And if it's below the threshold, we're going to say false. That's basically it. So let's see how this is done. So we get all the information that we analyze, and we split that information into 3 groups. One group we're going to use for training data. So this is the data that we're going to learn from. The second group, a smaller group, we're going to use for validation purposes. So the validation data set we use to calibrate the algorithm over the training data to achieve better performance. And the third group we're going to use to actually test if our crystal ball works or not. So in this particular case, our training will have 16,000 values. 4,000 values are going to be used just for validation, and 10,000 values are going to be used for testing to check if our crystal ball is guessing high income correct. So we separate the data set and we replace the categorical attributes high income, low income for 1 and 0. So basically what we call our positive class is low income. So our crystal ball will try to identify that you have a low salary. So if it says you have a low salary and you indeed have a low salary, that's what we call a true positive. And if it says you're going to have a high salary and you have a high salary, we're going to call this a true negative. So the positive class, it's low salary, and the negative class is high salary. And this is completely arbitrary. And then we create a model. So in this case, we are instantiating a logistic regression model, and then we're going to feed that logistic regression model with our training data. And the training data is split into all those attributes that we examined before: age, class, country, blah, 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 and the target variable: high salary, low salary. So after we have done this, we have created our crystal ball. And then we start doing predictions with our crystal ball. So we evaluate the accuracy of our crystal ball over the training data. So over the training data, we have 81% accuracy. That means if 10 people ask questions to our crystal ball, 8 of them will get it right. And for 2 of them, we'll get it wrong. If you break this crystal ball and try to look the inner sanctum, the inside, the guts of the crystal ball, what you're going to see in there, it's math. So we're going to see coefficients that will express the importance of that particular attribute for what we're trying to guess. So in here, it seems that education are things that contribute for us guessing if we're going to have a high salary or a low salary. Again, it makes sense, right? Okay, let's continue. So we need to have a baseline for compare if our algorithm is really good or bad. So one baseline that we can use is simply guessing, like throwing a coin. That could be a baseline. And if we are better than flipping a coin, that's already an improvement. If the accuracy of our algorithm it's worse than flipping a coin, we're in a bad place. But how can we be more scientific in terms of evaluating our algorithm? So one criteria is to do this matrix that sometimes is called the confusion matrix. And what this matrix is saying, it's evaluating that when we wanted to guess, if we ask the crystal ball for a particular person, does this person have a low salary? The crystal ball says it has a low salary, and the person indeed has a low salary. This is a true positive. So it's saying that for all the values that we have tested, 2,466, it's guessed a low salary, and it indeed was a low salary. So these are our true positives. And for 800 people, we guessed the high salary, and that person indeed had a high salary. So this is the perfect crystal ball working. It's happiness. It's a good place to be. But of course, life is not perfect. Our crystal ball will make mistakes. And these values, it's how we tune our crystal ball. because we either will tune our crystal ball for having more false positives or false negatives. For example, if in this case, our current crystal ball, our predictive algorithm, it's having a higher number of false positives because our positive class is low income. So we guessed low income, but it was high income. So we have 500 false positives. And we have 200 false negatives. We predicted a negative class, meaning high income, and it indeed was a low income. So this is something you can tune, and you can, if you invert the dependent variable, if you invert the classes you're trying to guess, this matrix will transpose, will flip. But how do you work to increase this value or decrease this value? You work on calibrating the threshold. So the threshold is the probability. We're working with a 50% probability. So we're saying that if you're working with a 50% probability, everything that is above will be our positive class. Everything is below will be our negative class. So if we change different values for our threshold, we move this line to the right, it means we'll be accommodating less red values, more blue values. So we're getting more true positives. So our false positive rate will decrease if we move this line to the right. So this is how you calibrate the curve. What else can you do? There are other criteria for you to try to calibrate this. So there is the ROC curve. So in the ROC curve is a different way to see the same concepts. You have true positive rate, false positive rate. So if you move to the right along this curve, you are increasing your true positive rate. If you go to the left and to the bottom, you are decreasing your true positive rate. So there is a good balance here. So it's another way to try to find the turning point on this curve for the best ratio between false positives and true positives. It's another way to kind of play with those values. Let's see what, oh yeah, and this was calibrating the model. So we were working with the training data set and with the validating data set. But remember that we have the testing data set, 10,000 values that we separate, they're clean, untouched. And those values are the ones that are going to validate the model. So we need to recreate a new crystal ball using now all the data that we use for training and for validation together. So we are learning now all of that data. And we're going to use the test data set as a final test to say, is it good or bad? Because it's usual for us to have a better results with the training data. And then when you use test data, we might have lower results. We had 81% accuracy. Let's see what happens when we run it against the test data set. So we do the same thing. And we're using the same threshold, and we're getting 81% accuracy on the test data set. That means our model is good. We can put that model into production. We're happy. These are some references. If you're interested to learn more about the confusion matrix, go over the mathematics behind logistic regressions, logistic regression or anything else. I hope you have liked, and we can discuss any doubts you might have through the computer science channel on Slack. Hope to see you in our next session. Au revoir. Bye-bye. Do widzenia.